Hello, today we're going to talk about Chapter 8, Section 1. So, Section 8.1, we're going to be talking about testing the difference between means when you have independent samples and sigma 1 and sigma 2 are known. So, I have three objectives for this section, and they are here. The first is we need to learn how to determine whether two samples are independent or dependent, because one of the independent samples. So we need to go back independent. Then we're going to introduce two-sample hypothesis testing for the difference between two population parameters in general, because this is what the entire chapter is about. And then lastly, we're going to learn how to perform a two-sample z-test. And as usual, we will have two different methods. The first method will be the critical value and rejection region method. And the second will be using p-values. And so the second one here is going to be with the calculator, right? The TI-80, your TI-84 calculator, whatever you have. And the first one will be via critical values and rejection regions. Okay, we also have, let me just kind of flip ahead here so that you can see, we have a corresponding, here we go. We have a corresponding form. This will help to kind of guide your computations and help you keep track of the steps of performing two-sample hypothesis testing. Okay, so let's go ahead and get started with our first objective, which is learning the difference between independent and dependent samples. Okay, so an independent sample is two samples are independent when they are collected from populations that are not related to each other. Okay, probably the easiest way to think of independent samples is that they are not dependent samples. And then what are dependent samples? Well, dependent samples are samples where each member of one sample corresponds to a member of another sample, the other sample. So for example, a classic case of dependent samples would be before and after. So for instance, if you were, say you collected data that might be, maybe you're doing a medical trial, a clinical trial or something like that, and you have, I don't know, blood pressure readings of 1,000 people before they take this experimental drug, and then you test them a month later after they've been taking the drug, and you have the same people, right? You have the same people in your test, and now you're able to compare those blood pressure results before the before the medical interaction and after, right? So you'd have 1,000 numbers in your first data set and 1,000 numbers in your second data set, and there would be a way to pair them before and after, right? Before and after you took the pill. Okay. So let's see here. This is a graphic representation of dependent versus independent samples. So notice here with the dependent samples, you've got a pairing. There's a way to associate each sample, right? Each element or each data point in the first sample with another data point in the second sample. And it doesn't have to be before and after. It could be, it might be that you're doing a study on twins, and so you have a bunch of pairs of twins, and one twin is in the first sample, and then that twin's twin is in the second sample, and so the pairing is the fact that they're twins, or it could be siblings, right? So there are all different ways to pair data. The key is that if the data is paired, then we're talking about dependent samples. If it is not, we are looking at independent samples. Okay, so let's do this example here. Classify the pair of samples as independent or dependent. I'll let you read it. Okay, so the answer is dependent. And this is a classic case, as I mentioned before and after, right? So you'll have 65 data points in your sample 1 and 65 data points in sample 2. And you can pair up the data points according to the person whose weight gives you, the before and after. All right, let's look at the second example here. Okay, so this is going to be a case of independent samples. Because there's no connection, there's no relationship between the 38 adult males and the 50 adult females, right? It just seems like they're two samples, but not that they're necessarily connected or related in any sense. Okay, so we've got that out the way. Now, assuming that you have independent samples, so assuming that you have two independent samples, let's learn about writing our null and alternative hypotheses for two-sample hypothesis tests. Okay. Typically, so we have the same setup. You'll have a claim. This time, instead of your claim involving just one sample, your claim will involve two samples. And your claim will involve comparing the two samples, right? So typically, a statistical hypothesis states that there is no difference, okay, between the parameters of the two populations, okay? So for instance, in the example I was doing before, perhaps you are, the manufacturer of the drug, or you're thinking about investing in manufacturing this drug, and there have been clinical trials, and so you want to see if the drug is actually effective in lowering the the blood pressure of patients. And so you might set up your hypothesis test, and your null hypothesis would be to assume that there is no difference between the blood pressure the blood pressure groups of well, that's not a good example because that was with the before and after, but we could still do a blood pressure example, and our samples could be male and female, or you could just take uh, control. You could take a control group and a group where you actually give them some type of treatment, and you would start off with the null hypothesis that there's no difference between the average, the average blood pressure, uh, of the groups, right? One group would be taking the pill and one group would be not taking the pill. And then you hopefully, if based on your evidence, you might be able to say, hey, no, actually, statistically, there is a difference. Taking that pill did make a difference, and so therefore I will invest in this company, or, or whatever. Okay, that's just an example that I thought of, off the top of my head. But as we do more examples, we'll see how to state the null and alternative hypotheses. Either way, right, the null hypothesis is always going to contain statements of equality. So equal to, less than or equal to, greater than or equal to. And the alternative hypothesis will include statements of inequality. Greater than, less than, not equal. Okay. So notice here that we're now working with two means. So you'll have mu1 and mu2. These are your population means. Okay, so you're performing a hypothesis test about two population means. So you'll have two population means that you're keeping track of. And then based on the claim, so the claim will make some comparison between these two means. Either mu1 is less than mu2 or mu1, all the different types of combinations of comparing mu1 and mu2. And based on the claim, you'll set up your null and alternative hypotheses. Okay, and now this is a key point here. Regardless of which hypotheses you choose, right, regardless of how your hypotheses end up, you're always going to assume that there is no difference between mu1 and mu2. So when you are setting up the conditional probability that you're computing, it is based on the assumption that mu1 is equal to mu2. Okay, now there are 4 conditions that are necessary to perform a z-test for the difference between two population means mu1 and mu2. Notice that if we are performing a z-test, then that means that we are assuming that we know sigma, right? And in this case, since we have 2 populations, we would need to know 2 sigmas. So we would need the population standard deviations of both populations standard deviations to be known. So in other words, sigma 1 and sigma 2 both need to be known. As always, we need to have our samples randomly selected. We need our samples to be independent. We have there's another test that we'll learn about, which is appropriate when you have dependent samples, okay? And the last is we're used to this last one here, which is the assumption that our populations are normally distributed, or each sample size is at least 30. So because we have 2 populations, that means we'll be taking 2 samples, right? And we need the samples to be randomly selected, and we need the samples to be independent. We need 2 different variables to keep track of the size of each sample. So we'll have N1 and N2, and this last requirement is saying if the populations aren't both normally distributed, then we'll need N1 and N2 greater than or equal to 30. Okay. So if these requirements are met, then the sampling distribution for the difference of the sample means is a normal distribution with, now this is, of course, as these 2 statements are a result of the central limit theorem. So remember, the central limit theorem discusses when sampling distributions are reasonably modeled by normal distributions. So our sampling distribution for the difference of sample means will be a normal distribution. And number 1, what is our new mean? Our new mean is just going to be the difference of the population mean. So when no difference is assumed, right? So if we're assuming that there's no difference between the population means, that is the same as saying we're assuming that mu1 minus mu2 is equal to 0. Okay, and then the second consequence of the central limit theorem is that we have a formula for the standard error. Now, the standard error for our sampling distribution for the difference of sample means is going to be given by this formula here. Okay, so this is kind of a way to combine the spread of each population, right? Because sigma 1 is going to give us information about how spread out population 1 is, and sigma 2 the same for our second population. So a way to discuss the spread of the sampling distribution for the difference of sample means is to use this formula here. Okay. So let's see here. So when we are performing our 2 sample z-test for the difference between means, population means, we will have our test statistic. It's just going to be the difference of our sample means, and we will have the standardized test statistic. Now remember that we'll be assuming that mu1 minus mu2 equals 0 when we're performing our hypothesis test, right? So remember that when no difference is assumed, the mean is 0, right? That difference in means is 0. And that's because, regardless of which hypothesis you'd use, you always assume that there's no difference between the population means, aka mu1 is equal to mu2. And then what's another way to say mu1 is equal to mu2? Mu1 minus mu2 equals 0. Okay? So it's all tying together here. And then we have here repeated the conditions under which we can use the two sample z-test. Okay. All right. So in words, we have exactly the same procedure as we did in chapter 7. Okay. So number 1, the first thing we want to do is we want to verify that we can use the test. Number 2, we want to set up the hypotheses, the null and alternative hypotheses. Number 3 is we've got to figure out alpha. And then number 4, let's see here. 4, 5, and 6. Now, if we are using the critical value and rejection region method, then these are the 4, 5, and 6 steps that we'll use. Otherwise, we will use technology, the one prop, not one prop, we're working with 2 samples, right? So we'll be using 2 samp z test on the calculator. Okay, and then as a result of that, either way, right? So either method will give us either we'll get a p-value. So if we use 2 samp z-test on the calculator, this will give us a p-value. And if we do the critical value and the rejection regions, we'll end up with the rejection region and the standardized test statistic, right? And so then we can make a decision to reject or fail to reject. And then the last step is to interpret the decision in the context of the original claim. Okay, so let's get started with an example. So a credit card watchdog group claims that there is a difference in the mean credit card debts of households in California and Illinois. The results of a random survey of 250 households from each state are shown at the left, actually in the bottom here. The 2 samples are independent. Assume that sigma 1 is 1045 and sigma 2 is 1350, so this should actually be sigma 2. Do the results support the group's claim? Use alpha equals 0.05. Okay. So let's get started here. The first thing we want to do is we want to verify that we actually can perform our 2 sample hypothesis test. And what we need to verify, we've got 4 things that we need to verify. The first is that sigma 1 and sigma 2 are known. So I'm just going to use the highlighter here. And this is very clear from this right here. Sigma 1 and sigma 2 are known, so we can verify that. The second thing we need to know is that our samples are independent. So the 2 samples are independent. We've got that. The next thing is that we need to know that our samples are random. And that is true because the surveys were random. And the last thing, let's see, what's the last thing we need to do? Okay, either the population is normally distributed or N1 and N2 are greater than or equal to 30. Okay, so let's just check that. And indeed, N1 and N2 are greater than or equal to 30. So we're good. Okay, so we verified what we need to verify. And now step 2. So those 4 items. We did that. Step 2 is going to be to set up the null and alternative hypotheses. And the way we set those up is we first start off by writing out the claim. What is the claim? The claim is, let's see if we can get the claim. The claim is there is a difference in the mean credit card debts of households in California and Illinois. Okay, so that's our claim, is that there is a difference in the mean credit card debts. So what are our population parameters that we're concerned with? So our population parameters, we can say we've got mu1. We can let mu1 be the mean credit card debt of households in California, and then mu2 can be the mean credit card debt of households in Illinois. Okay, so according to the statement of our claim, right, so our claim is that there is a difference in the mean credit card debts of households in California and Illinois. We're saying that mu1 is not equal to mu2. Okay, so writing that in math, we would say mu1 is not equal to mu2. This is our claim. And now we're ready to, the next step is we need to write the complement of this statement, right? So this is a mathematical translation of the verbal claim. What is the complement of this mathematical statement? Excuse me, mu1 equals mu2. Okay, and now the last thing is we need to figure out which is our H0 and which is our HA. And it turns out this time that our claim is HA. Okay, so we've set up our H0 and HA. We're good with that. The third thing we need to do is we need to figure out alpha. And alpha is given in this problem here. It says use alpha equals 0.05. So alpha is going to be 5%. So alpha equals 0.05. And now if we are doing rejection region, then let's see here. So we're going to, in this example, let's do rejection region method. Okay, so now alpha is equal to 0.05. From our HA, we can tell that we need to do a two-tailed test, right? So we need to perform a two-tailed hypothesis test. So we need to figure out, so we'll have something like this. And we need to figure out those critical values. How do we figure out the critical values? Well, we know that this area is going to be equal to 2.5%. So it needs to be 0.025. And this area, this cumulative area, is also going to be equal to 0.025. So to get this number, since this is a z distribution, I'm going to, that's going to be negative ZC, this is going to be positive ZC. So negative ZC is going to be equal to inverse norm of, my cumulative area is 0.025. My mean is 0 and my standard deviation is 1. And that's going to give me, let's see here. So I need to go to second vars to get to my distributions. Inverse norm, 0.025. Okay, paste. And I get negative 1.95 99. Okay, so my critical values are plus and minus 1.9599. And my rejection region, therefore, is any number that is less than the negative 1.9599 or greater than negative 1.9599. So I've got my rejection region here. Okay, so my rejection region number less than negative 1.9599 or greater than 1.9599. Okay, next thing I need my test statistic. I need my standardized test statistic, really. Standardized test statistic. Let's see here. So what was the formula for the standardized test statistic? Because once I figure that out, I'll see if it falls in my rejection region. Okay, so that's the idea behind that. Here we go. Here's my formula for the standardized test statistic. And it is, let me write this down here. So I need x1 bar minus x2 bar minus mu1 minus mu2 all over my standard error. And my standard error is going to be the square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Okay. So let's go ahead and get this written down. So my standardized test statistic, z equals, I need x1 bar minus x2 bar minus, so this is my test statistic, minus mu1 minus mu2 over square root sigma 1 squared over n1 plus sigma 2 squared over n2. Okay, and so this is my sample difference in means. This is my hypothesized difference in means. And this is my standard error of the sampling distribution of difference in means. Okay, so let's write this out here. So this will be equal to my x1 bar minus x2 bar is going to be 4777 minus 4866 minus mu1 minus mu2, that's just going to be 0, divided by the square root of, now my sigma 1 is 1045, so I need 1045 squared, and n1 is 250, plus my sigma 2 is 48. No, sorry. Sigma 2 is 1350 squared over 250. Okay, now I kind of want to I need to mention that. So now I'm not sure if I mentioned this before, but in terms of verifying these 4 items, I need to mention that we actually do have independent samples, okay? And why are the samples independent? Because one sample comes from credit card debts in California, and another sample comes from credit card debts in Illinois. And so there's no connection between the households in California and the households in Illinois. Okay, so this is actually an important example where N1 and N2 are the same. They're both 250. So even though N1 and N2 are the same, our samples are independent, right? Because it's not like each household in, there's one household in California that's linked up with another household in Illinois, right? They just happen to be two samples of the same size, but the samples are independent. Okay, so now what do we get when we do this? Let's see here. So we should get, this is going to be approximately negative 0.82. Okay, so what I get on my calculator is I get 4777 minus 4866. Okay, so so this numerator here is going to be 80. That's going to be negative 89. And then for the denominator, I need 1045 squared over 250. Okay, so this is 4368.1. And now 1350 squared over 250. This is 7290. So I've got negative 89 over the square root of 4368.1 plus 7290. So this is going to be, let's see here, negative 89 divided by the square root of 4368.1 plus 7290. Yes, it's negative 0.824282578. Okay. So I've got my standardized test statistic, and now it is time to see if it is in my rejection region. So I'm now at the step of making a decision. So this is number 5, make a decision. And let's see here. So looking at it, what is we said that this critical value is negative 1.9599. And our standardized test statistic is negative 0.824. Okay, so that is clearly not going to be in my region, because that's like maybe over here, negative 0.824. This is my test statistic, standardized test statistic. So my decision is to fail to reject. Why? Because my test statistic, standardized test statistic, is not in my rejection region. So my decision is fail to reject H0. And the last thing I need to do is interpret my decision. And here's the interpretation. Now I failed to reject H0, and my claim was HA. So at the 5% level of significance, there's not enough evidence to support the group's claim that there is a difference in the mean credit card debts of households in California and Illinois. So at the 5% level of significance, not enough evidence to support the claim that there is a difference in average credit card debts of households. In California and Illinois. Okay, all right. So now let's do another example here. So in this second example, we're going to use technology to perform a 2-sample z-test. And I'll give you a moment to read the problem. So now since the steps are very similar, I'm going to skip number 1, which is verifying that let's see here. Let's actually, what I want to do is, we're going to get to this part here where we state the claim mathematically and verbally. Okay, so verbal statement of the claim is going to come from here. So claims that the average daily cost of meals and lodging for vacationing in Texas is less than the average daily cost in Virginia. So the claim is that, verbally, is that the average average cost in Texas, Tejas, is less than average cost in Virginia. Okay, now to translate mathematically, average cost in Texas, based on our notation here, Texas, do you see how everything here is involving 1, x bar 1, mu 1? So then x bar 1 and n 1. So mu 1 must be the average daily cost in Texas. And then we want mu 2 to be the average daily cost in Virginia. Just so we can keep with the standard, right? So if everything revolving around Virginia has a 2 subscript, let's go ahead and carry that through in our notation. So stating the claim mathematically, we'll say mu 1 is less than mu 2. Okay, now we need to write the complement. So mu 1 less than mu 2, that's the claim. The complement is going to be mu 1 is greater than or equal to mu 2. And this is also going to be our null hypothesis. So our alternative hypothesis is going to be the claim. So the claim is the alternative hypothesis. Our null hypothesis is mu 1 greater than or equal to mu 2. Alternative hypothesis, mu 1 less than mu 2. Specify the level of significance. This was 1%, 0.01. Okay, and that was given in the problem. We are conducting a 2-sample z-test. Why? Because, and here we go, state the distribution. Because sigma 1 and sigma 2 are known. So state the distribution used in the test. We're using a z distribution. What are the requirements for this test? So number 1, we need to have random samples. We need to have normally distributed populations. Or sample sizes greater than or equal to 30. We need to have independent samples. And what else do we need? We need to have sigma 1 and sigma 2 known. Is that everything? Let's just verify that that's everything. Okay. So verify the sigma 1 and sigma 2 are known. Samples are random. Samples are independent. And either the population is normally distributed or both sample sizes are at least 30. Okay, good. We didn't forget anything. Now, random samples, that is stated in the problem. How do we know this? We know this because let's see here. Table left shows results of a random survey. So that's one thing. The two samples are independent. That's another thing. Both populations are normally distributed. That's another thing. And then the fourth thing is that sigma 1 and sigma 2 are known. That's the last thing. Okay. So, for all of these are stated in the word problem. And then just to indicate that this is the one we're using, we'll highlight that we're doing normally distributed populations. Okay. Now, find the standardized test statistic and the p-value for this test. Here we go. Here's our fun part. So on the calculator, on your calculator, you're going to go to Stat, then go over to Tests, and then go to 2SAMP Z-Test. And there's a video on how to do this in the links in Canvas. So we're going to go to Stat, go over to Tests, and then you want to go to 2SAMP Z-Test. For me, that's number 3. And now your input, we're going to input statistics, right? So between data and stats, we're doing statistics, so select that. And then sigma 1 is going to be 1045. Sigma 2, just kidding, sigma 1 is going to be 19. Right? So sigma 1 is 19. Sigma 2 is 24. 19. Sigma 2 is 24. X1 bar is 234. Okay, N1 is 25. X2 bar is 240. N is 20. N2 is 20. And then we have to go to our alternative hypothesis here. This is going to tell us what to select. So let me just go ahead and copy this down here. So sigma 1 is 19. Sigma 2 is 24. X bar 1, 234. N1, 25. N2, 240. No, X bar 2. N2, 20. And now it says mu 1. Now do we want not equal to mu 2, less than mu 2, or greater than mu 2? We want mu 1 is less than mu 2. So let's select the less than mu 2. Okay. And then you're going to hit your down button, and then we're going to go to calculate. Hit enter. Okay. So what is my output? My output is, it says mu 1 less than mu 2, just as a reminder. Z equals negative 0.912448597. P equals 0.18076627795. And then X1 bar 234, X2 bar 240, N1 25, and it has a little down arrow. So this is my output. From here, I'm going to be able to have my standardized test statistic. So let's copy. I think that's one of the problems. What is the standardized test statistic? Paste. Okay. What is the p-value? That is also here. So my probability value is going to be here. Copy. p-value, paste. And one or two complete sentences, explain what the p-value means for this problem. So here's what it means. It means that the probability of selecting a sample, a random sample, with, not a random sample, two samples, two random samples with a difference with sample means difference as extreme or more extreme than, what was our sample mean difference? Our sample mean difference would have been x1 bar minus x2 bar, so 234 minus 240, which would be -6. So -$6 is, what is the probability? Is 0.18076. Okay. Now let's go ahead and sketch. And we said that we will need to have a left-tailed. How can we tell it's left-tailed? We'll need to have we're performing a left-tailed hypothesis test because we received this information from the alternative hypothesis. So I have a left-tailed test, and so this is our difference. So this is, we're actually doing, let's see here. So we'll say our left-tailed, our standardized statistic here is negative 0.9124. So it'll be like right here. And now this area equals 0.1807. Okay. And that value is negative 0.9124. Okay. All right. Now make a decision to reject or fail to reject. Well, that is a very high p-value. So since p is alpha greater than alpha, we're going to reject. No, sorry, fail to reject. So we're going to fail to reject H naught. Reason for decision, because p-value is greater than alpha. And interpret the decision in the context of the original claim using complete sentences. Okay, here we go. So at the 1% level of significance, there is not enough to support the travel agency's claim. Okay. So this is a summary of what we've done today, and thank you.